In this video, I want to show you how to calculate the gradient in spherical coordinates, how to find the expression of the gradient written in spherical coordinates. It's an exercise that can also be done in multivariable calculus, but I think it is worth re-examining the math by using also tensor notation and matrices as well. So let's see how we can do that. In particular, the gradient of a function can be written in index notation, like the derivative of f with respect to xj. So j is the index. We have x1, x2, x3, and they can be thought of as x, y, z. In the new coordinate system, we have new variables x1 prime, x2 prime, and x3 prime. So in a spherical coordinate system, we have r, theta, and phi. And therefore, in that case, the gradient, or in particular, the partial derivatives, which are not the gradient, because the gradient is a vector, we will see that the expression for the gradient is not simply df over dx prime j. So x prime j is a concise way to keep track of these three variables, which are none other than r, theta, and phi. So these are the partial derivatives with respect to x prime j, but this is not the gradient. We can also write it in a different notation, df over dx prime vector. So instead of writing the index notation, I'm using the arrow to symbolize the fact that this is indeed a vector. So this is a vector, we are taking the derivative with respect to a vector, and we get a vector. So for example, in Cartesian coordinates, we have df over dxj, which can be represented as a column vector of the kind df over dx, df over dy, and df over dz, like this. And we can also rewrite this by using the chain rule, so we can write dx vector with respect to x prime, and then we have df dx. So basically this is the vector, this vector here, whereas this is the Jacobian matrix. This is a matrix because we have the derivative of a vector with respect to a vector. That gives us a matrix. It's easier to think about this in index notation. This would be dx I, dx prime j, and then here we have df dxi, like this. So this j here is an index that spans the three rows of the vector. So we have the first row, second row, third row, because this is a column vector. And therefore here, when we write this matrix, this is some matrix J, which is the Jacobian matrix. So let me put a tilde below the matrix to denote the fact that indeed it is a matrix. I'm using the tilde notation there. And then it has other two indices, Ji, so don't confuse this J with the matrix J, of course. And then here we have df over dxi. So this is still a column vector. So when we change I, we are moving from one column to the other inside the matrix, which is a 3 by 3 matrix. So we are moving like this when we change I, whereas when we change J, we are moving in this direction, so along the column. So we are changing rows. So it is simply the usual rules. These are the usual rules for matrix multiplication. And it is just useful to remember that, because this will help us while doing the calculations. I will let MATLAB do the calculations, but it is important to understand the formulas that I'm writing down here. Then let me write the gradient of a certain scalar function f. This can be written in the following notation. I have unit vector t sub I df over dxi. So I'm summing over I, and this is a unit vector along the I direction. So we have t1, t2, and t3. And in Cartesian coordinates, these are just I, j, and k. The unit vectors I, j, k. So t1 would be equal to I, t2 would be equal to j, and t3 would be equal to k. And this is something that I've already discussed. It's basically this vector here. Now, this is a vector, and there are three of such vectors. So this can also be thought as a matrix. I can also call this T sub tilde. So T tilde would be a matrix of the following kind. So we have in the first column we have T1, in the second column we have T2, in the third column we have T3. So we might have I, j, and k, and if we write the components of I, j, and k in the usual, with respect to the usual axis x, y, z, this would basically be just the identity matrix. It's easy to realize that. And then here I have df over dx vector. So in this notation I have to write it like this because this is a matrix and this represents the vector, the column vector. This can also be written in spherical coordinates, but in that case we have a transformation rule for t, and we also have a transformation rule for the partial derivatives. The transformation rule for the partial derivatives is written here. In particular, df over dx prime is equal to this Jacobian matrix, which is called J, and then we have df over dx. So from here we can also write df over dx equal to J inverse df over dx prime. The Jacobian matrix can be calculated quite easily. Let me mention how to calculate it. The formula is basically this one, but let me be more explicit than that. It can be calculated like this. So the derivatives of x, x is the vector x, okay? So it has the components x, y, and z. X is basically the usual function of r, theta, and phi in spherical coordinates. So I'm using a spherical system such that if we have the radial vector r, the projection of r on the xy axis, on the xy plane, is the following, and this angle is theta, whereas the so-called polar angle is phi. This is the angle measured from the z-axis, so it's the angle between r and the z-axis, whereas theta is the angle between the x-axis and the projection of r on the xy plane. So x has the following expression. It is equal to r cosine theta sine phi. Y is equal to r sine theta sine phi, and z is equal to r cosine phi. So j is this expression here. Remember that I, when we change I, we are moving in this direction. So we have dx with respect to x prime 1, which is r. Then we have derivative of y with respect to r, derivative of z with respect to r. And similarly, in the second row, we have dx over d theta, dy over d theta, dz over d theta. Then we have dx over d phi, dy, d phi, dz, d phi. And this can be calculated, so these derivatives are quite easy to compute once you have the expression for x, y, z written in spherical coordinates. So the expression for this matrix is cosine theta sine phi. Then let me create this grid so as to make sure that we separate the terms. So we have, this is the 1-1 entry. Then this element here would be this element here, dy dr, which is sine theta, sine phi, and then we have the cosine of phi here. Then here we have minus r sine theta, sine phi. Then here we have r cosine theta, sine phi, 0. And here we have r cosine theta, cosine phi, r sine theta, cosine phi, minus r sine phi. And so here we have j. We can define it. I also define it in MATLAB later. And from that we can calculate j inverse. I will not do it by hand. And another thing that we need to do is we need to transform t into t prime. And what is t prime? So t prime, I will define it to be the matrix given by r in the first column. And then we have theta, and these are the unit vectors in the spherical system. And then we have phi in the third column. This can be also written as ijk times the matrix which defines r, theta, and phi with respect to I, j, and k. So first let me write it and then I will be a little bit more explicit. So I have the cosine of theta, sine phi, minus sine theta, cosine theta, cosine phi, sine theta, sine phi, cosine theta, sine theta, cosine phi, cosine phi, 0 minus sine phi. So this is basically a matrix that I will call E. This matrix here is what we previously called T tilde, and this is T prime tilde. So what this tells us is the following. So basically R is equal to I times this first element, so I have cosine theta sine phi, plus j times this first element, this second element here, sine theta sine phi, plus k times this cos phi, and this is simply the radial unit vector along the direction r. It is quite easy to see that. Then we have the unit vector along the direction theta. This can be calculated by you simply taking the derivative of r with respect to theta, and r in this case is the unit vector r, so it's this vector here. If we take the derivative with respect to theta, we are going to get a vector along theta, but we also need to make sure that the norm of theta is equal to 1. And in order to do that, one can see that you have to divide this by sine phi. So it is quite easy to see. If you take the derivative of this with respect to theta, then you have to divide by sine phi in such a way to make the norm of this vector equal to 1. And once you do that, you get exactly these vectors multiplied by this column here. So you get minus sine theta times I plus j times the cosine of theta, like this. And finally, you can also calculate the unit vector along phi. One can show that this is given by dr d phi, and there is no factor here in this case, because when you take the derivative, what you get from that is already a unit norm vector. And so basically you simply have to take the derivative of this with respect to phi, and it's also quite easy to see that this will be given by these vectors multiplying this column here. So you get cosine theta, cosine phi I plus j sine theta cosine phi minus k sine phi. So here I simply wanted to tell you more about these relations here, and what we really need is the following. So we need t tilde prime equal to t tilde times the matrix here. So let me also put a tilde here to denote the fact that this is a matrix. Now we have all the elements in place. I want to substitute the expressions that we found in here. So we found that t can also be written as t tilde prime times E inverse. So I have rewritten this expression as t tilde equal to t tilde prime E inverse. So that we have t prime here, which are the unit vectors along the three axes in the case of spherical coordinates. That's why we need t prime here. Then another thing that we need is to convert these partial derivatives in terms of the derivatives d over dx prime of f. And to do that, we use this formula. So here we have j tilde inverse. And so this is, remember that this is the nabla operator applied to f. And this is the formula that I'm going to implement in MATLAB. That will allow us to find the nabla operator or the gradient operator in spherical coordinates, to find the nabla in spherical coordinates. And basically, we simply have to implement this part of the formula in MATLAB, because once you find this, remember that you're going to multiply that by t tilde prime, but t tilde prime are these unit vectors. So this would be a column vector with three components, and therefore the first component here will be multiplied by r, the second component here will be multiplied by theta, and the third component here will be multiplied by phi. So the result of that, I mean, if we read these three components, we really have the gradient in spherical coordinates. So let's do that. I have defined j here. I have defined e here. So you have to calculate the inverse matrices, these inverse matrices, and then I have to multiply them by df dx prime. Remember that this is equal to df over dr, df over d theta, and df over d phi. So I can do these operations. Let me show you. I have prepared this simple script. And so I defined the matrix E. I define all the components. I also define the matrix J. And before doing that, I also define this df here is basically, let me show you, it's the gradient. It's not really the gradient. Those are the partial derivatives. It's the vector of partial derivatives with respect to the coordinates that we have in spherical coordinates. So we have df dr, df d theta, and df d phi. So since in this case, as it is defined here, this is a row vector, in the final formula, I need to transpose it to get a column vector, because remember that here we must have a column vector. And here, what I'm trying to highlight is that we are taking the transpose of df, and in MATLAB, you take the transpose like this. So you put this dot and then the apostrophe. And then I multiply by the inverse of j and the inverse of e, and I simplify the result. And that's basically it. So you can see the result. So the first component of the gradient is the following, df over dr. The second component of the gradient in spherical coordinates is the following, df over d theta, and then you also have to divide by this factor, r sine phi. And the third component of the gradient is df over d phi, so df d phi, and you divide by r. Let me also save this, because I have not saved this script. I can call it nabla, spherical, something like that. And that's it.